Okay, this is lecture 20 for continuity equation. So today we will talk about Schaffer-Gummel scheme. So I think that we have already covered this one. So importance of a Schaffer-Gummel scheme cannot be overemphasized. So it is the single most important topic in this course. So now let's go to the derivation. So previously we stopped here, and now it's time to start the derivation. Basically, the Schaffer-Gummel scheme is a 1D approximation. You must understand this one. And when we write down the electron continuity equation in one-dimensional space, we can write down in this way. So of course, you can reconstruct the three-dimensional version quite easily. And y q dn. However, in the case of Schaffer-Gummel scheme, we always take this 1D approximation. So it means that let's consider one special case like hexagonal. mesh in your mind. Let's see that this is your two-dimensional mesh you wanted to consider, and it has 6 red dots corresponding to neighboring node. So in this case, what we can do with this one-dimensional approximation is quite obvious. So if we are really in 2D, then we must calculate a certain flux over the volume, or in this case over triangle. But instead of that, we just assign our flux on the edges. So edge, the line segment connecting these two nodes. So we try to assign a flux, another flux in this way. Of course, these fluxes are just one-dimensional quantity and they are directional. So in this case, we have no idea about component perpendicular to this edge. So we always try to calculate the flux aligned to the edge direction. So once we calculate this K in this way, then obviously we have no idea about what is the actual value of flux here and there and there. However, fortunately, with the help of box integration, or called as finite volume method, then we can generate a certain integration box for this system. So maybe you remember this one if you have attended our previous lectures. Then, okay, so it's not very much visible. Yes. So now we can find that this is the area of our face perpendicular to this edge. So first calculate the flux between these two nodes and multiply the area of a perpendicular face. Then that will give us the integrated form of our electron continuity equation. So we can effectively avoid the question like what is the value of a perpendicular component of electron flux defined on this edge. This kind of questions can be avoided effectively. So that's the reason why we are allowed it to calculate this 1D approximation. So the question we have is always, what is the flux, one-dimensional flux between these two nodes or another two nodes, so we can make it as simple as possible. So now let's adopt that. We have 1D approximation. So now from the continuity equation and the current continuity, we can say that in 1D case, actually we must have divergence of Jn vector equal to 0. Yes, that's true. However, in the case of one-dimensional case, this one just becomes one-dimensional derivative, and since the derivative vanishes, so it means that Jn is a constant over the H. So that is an important observation. So please remember our previous trial for discretizing the continuity equation. So have you considered such kind of observation? Actually not. What we did in the previous case was just to individually consider the approximated form of this first derivative and first derivative and estimated value of electron density. That was all. There is no guarantee that the electron current density is constant over our simulation domain or our line segment. However, in the case of our new approach called Shapeto-Kuhn scheme, we introduce this assumption. Here, although Jn is a complex function of electron density and electrostatic potential, but we will introduce a certain assumption that Jn is a constant. So in order to make it a constant, what should we do? We should change our electron density and electrostatic potential dynamically to fit the constantness of J sub n. So by applying this assumption, so now a simple approximation about electrostatic potential and electron density is no longer used. Instead of that, we will just try to find out the form of electron density. Of course, here we have two unknown variables. Here we have electron density and electrostatic potential. So therefore, in order to make it constant, in order to make J sub n a constant, then they, electron density and electrostatic potential should, so pencil is stuck, so let's wait for a while. Okay, so in order to make it a constant, Jn equal to some constant, we must have the appropriate form of electron density and electrostatic potential. However, here we have made another assumption like linear approximation for electrostatic potential. Even in this Shapeto-Kuhn scheme, we still consider electrostatic potential as a linear function, linearly varying function over the line segment. So maybe you can ask me this question. Okay, so you wanted to just make an accurate solution. But why do you introduce such kind of approximation once again? No, here we have electron density and electrostatic potential, and more or less, even in the physical sense, they are really linear. And in the case of electron density, they are really having non-linear behavior. So maybe we have talked about this one once again. So we have talked about this one previously. For example, xi plus 1. Let's say that electrostatic potential is linearly varying, and let's assume that we are talking about the equilibrium electron density. Then equilibrium electron density can be expressed as this simple form, exponential of electrostatic potential. So although electrostatic potential itself is a linear function, however, our electron density can show exponential behavior. So although this is true although this can be well approximated as linear approximation, however, it will make drastic failure when we make it as a linear function. So that's the reason why here we have two functions, 1 and 2, and if we take both of them as unknown variables, then it will be quite much complicated, and this is only one single equation, so we can have only one single unknown variable. So which one should be taken as unknown variable and which one can be approximated? The obvious choice is this one with given node values, boundary values. This one can be well approximated as a linear function, and under the approximation of linearly varying electrostatic potential, we wanted to calculate the form of electron density. That is our two assumptions. So once you understand this assumption, the remaining discussion becomes quite easy. So please think about these approximations, and if you have any question, then please feel free to ask me any question. So you are now asking this one. Yes, so I will explain right now. Okay, so his question is about this right hand side. So let's go to step by step way. So now yes, so Jn is a constant now, and this one is constant, and now we have really position dependent quantities like electron density. Okay, it is quite much position dependent, and this one is also quite much position dependent. And now let's think about the remaining quantities. What is it? This one is a QDN and this is a Q mu n. However, fortunately, we understand there is a certain relation between our diffusion constant and mobility. So what was it? That was so-called Einstein relation, and there was the proportional coefficient of the summer prodigy. So simply speaking, we can just say that this can be written as Q times dN over Vt. So that is written here, and we can pull out this Q dN from this diffusion term and drift term simultaneously. So now we have here, this one is written as this form. This is originated from diffusion term, and this one is now written as here. It is originated from drift term, and now we have QDN in this part. So up to now, everything is so clear, and we have considered that this Jn is a constant. But that doesn't necessarily mean that this one is also a constant. But we assume that dn is simultaneously mu n. This is a function defined over the segment, the line segment called as an edge. So they are constant once again. So simply speaking, here and there we have a certain line, and we assign a single quantity to this line. Yes, this line has a certain values of this of n. Well, it is really questionable. For example, let's say that this point we have doping density like 10 to the 20, and here we have a doping density like 10 to the 16. Let's assume one specific case. Then please try to expect what will happen to the mobility of these two nodes. So what we can expect is, since we have quite a high density of impurities, so mobility assigned at this node can be quite low due to the impurity scattering. And in the case of this right node, we have a relatively low density of impurities, so it is not that much affected by what? Affected by the impurity scattering. So maybe UN can be quite high. So simply speaking, it can be orders of 1000, and it can be orders of 100 or 10 in the same unit system due to the impurity scattering. So natural question is, then how can we assign certain average mobility value into this part? Okay, so although we can have quite much different values of mobility, but still we wanted to introduce a certain value. The simplest way is just take half of it. So we have a certain mobility and another mobility, then we can make the just arithmetic mean to get the average mobility. So anyway, of course, things are not as easy as this way. If we consider 2D or even 3D cases, how can we assign certain mobility value to an edge, given edge? That is really a big problem. But right now, we will just assume that dn or mu n, although in principle they can be functions of position, but still the entire term, this term, will be considered as a constant. So here we have a small approximation of a constantness of this mobility or diffusion constant. Okay, so is it sufficient for you to understand this, the situation? Okay, so now once we accept all of these kinds of approximations, I do not say that these are all accurate and precise, but I'm saying that these are assumptions used to derive the Schappeter-Gummel scheme. So once we adopt these kind of approximations, then now let's revisit this equation once again. Now we understand n is a unknown variable and we have a first derivative with respect to the position. And here we have also the linear term of electron density, and here we have certain coefficient. In principle, they can be once again position dependent, but fortunately, this coefficient is regarded a constant. And right hand side, in this right hand side, you can find also a constant as a source term. So simply speaking, now this equation can be regarded as linear first order differential equation for our unknown variable n. Then now what you can do is quite easy. First of all, you can just set this right hand side as 0, then you can find certain homogeneous solution. After that, you just recover this constant term, then you can make also inhomogeneous one. So that is quite easy to solve this kind of simple linear first order derivative equation, the differential equation. So this is nothing but first order differential equation with linear coefficient. So that is important. Linear coefficient. So now the solution has the following form. So here we have exponential term. Why do we have it? So when we make this one into it, then the first derivative just gives us n times, so 1 over vt and delta phi over delta x. So we have a certain term, and now that is perfectly cancelled out by our linear term. So we understand this C1 related term. So C1 related term is corresponding to the homogeneous solution. After that, we have another constant here because our right hand side is a constant. So now we can introduce this one. When C2 is also submitted here, then actually dn over dx does not contribute to anything. So we will have just 1 over vt and delta phi over delta x, C2 equal to jn over qdn. So now you can understand this C2 is nothing but just reformulated name of our current density because they are all constant. These are all constant. So simply speaking, C2 is proportional to Jn. Obviously, our ultimate goal is what is Jn? How can we express this Jn with a function of boundary values like electron density defined at x sub I and x sub I plus 1, and electrostatic potential defined on phi sub phi defined at x sub I and x sub I plus 1. So therefore calculating this C2 will be quite important. Once we know C2, then just multiplying this number, then we will get the J sub n. So now let's try to fix the value of our undefined or undetermined coefficient like C1 and C2. Okay, so do you have any question up to now? Once again, please feel free give me any question. So You are really encouraged to do that. So then we must find out two constants, undetermined one, C1 and C2, but they should satisfy these conditions. This is nothing but we know the Hg value or boundary values of electron density. So now let's try to just insert this condition. For example, if we follow this first line, simply n sub I equal to C1 exponential, yes, nothing but here we have 1 over Vt delta phi over delta x, yes, and xi plus C2. Then if we just introduce another condition, then we will have just plus 1 and we will have plus 1. We have two quite similar equations, so taking the difference can give us something. So what happens if we take the difference between these two, n sub I and n sub I plus 1, then we can say that n sub I plus 1 minus n sub I is given by this C2 is gone because C2 is shared by this n sub I and n sub I plus 1. The remaining thing is just C1 times exponential of blah blah xi plus 1 minus C1 times exponential of another constant n xi. Everything is the same. Even the C1 is the same. Then we can say that this xi plus 1 can be expressed as xi plus delta x. So, are you with me? So now, if we adopt this form, then simply speaking, we can say that C1 times exponential of something xi, also exponential something delta x minus C1 times exponential something xi. That is the form of the difference between two electron densities. Unfortunately, we can find common factor of C1 exponential, C1 exponential. So simply speaking, what we can have is our electron density difference is given by C1 exponential something xi multiplied by, now we have exponential, now let's write it down explicitly, 1 over Vt delta phi delta x and delta x minus 1. So are you with me? Then you can immediately understand, since this is delta x and this is also delta x, they are cancelled out. Then here we have the argument of our exponential function becomes really simplified. Simplified by what? Simplified as just delta phi normalized by 1 over Vt. So now you understand. This relation. This relation just gives us a hint for what is C1. Now C1 coefficient can be written as this ni plus 1 minus ni divided by what? All kinds of this complicated thing. Wow. So we have exponential something xi and exponential once again delta phi over Vt minus 1. That is the form of our C1. Let's visit my slide. Okay, So I'm just summarizing here the previous discussion. So C1, oh sorry about that, n sub I and n sub I plus 1 are explicitly shown here. We just take the difference. So now we can pull out the common factor, and the remaining thing is much simplified. Exponential of normalized electrostatic potential difference. This is electrostatic potential difference, and that is normalized, and take the exponential function minus 1. Now we know C1. What is the C1? C1 is shown here. This is the form of our C1. Please note that our ultimate goal is not to calculate the C1, but we wanted to eventually calculate C2, because once we know C2, then this is proportional to Jn. In order to calculate the current density, we must understand the form of C sub 2. Okay? Any question? Once again, if you have any kind of question, then please let me know. So I will be quite happy to listen your question. Then now let's go to the one. Okay, now our ultimate goal is to calculate C2. Then how can we calculate C2? Yes, this is nothing but C2 is given by the difference between this and that. And now we know C1. So let's just insert newly found C1 form into it. Then eventually we can get the C2. So this is nothing but C2 can be calculated by the difference between n sub I and this form. Although looks complicated, but this is not a function. This is a boundary value, and this is a boundary value, and this term is constant and exponential. You know it, and C1 also you know it. So by using C1, what was the form of C1? Yes, that was C1's form was please. Is it this one? So C1 has an difference of n times something. So now let's put it here. Here we have the exactly same form. Exponential blah blah times x sub I. And you can find that also here. Exponential blah blah and x sub I. So they are cancelled out by multiplying this factor. Then the remaining thing is this guy and this guy. So that's the reason why our C2 looks much more simplified than expected. So this looks quite a complicated term. Now just to reduce this term. Now let's just split the dependencies on the n sub I and n sub I plus 1. Here we have number 1, coefficient 1, and here we have 1 over exponential minus 1. So this is the coefficient. How did we calculate it? So for n sub I, we have the terms like 1. Then we have another thing like exponential something minus 1, 1. So it becomes exponential something minus 1, exponential something minus 1, and plus 1. They are cancelled out. that's the reason why we have this form. And for n sub I plus 1, we just took it here. Yes, so minus 1 over exponential minus 1. So that's it. Now we have the C2 function. How about your feeling about this form? Well, it looks quite complicated, but yes, I agree with you. At a first glance, it looks quite much complicated, but please note that this is boundary value. This value is known. This value is known. Also, this value is known, and this is boundary value. Although looks quite complicated, but C2 is nothing but a function of boundary value, and potential difference delta y. It is not that difficult to actually calculate this C sub 2. So what is this B? I think that I made mistakes here. So Jn should be proportional to not B, but oh yes, C sub 2. So previously I used the notation like B, but I changed it to C2, so sorry about that. Now we have this form. So we can just multiply this leading coefficient into our C sub 2, then eventually we will have the form of J sub n. That's it. So this is the, simply speaking, this is the electron current density approximated with the Schappeter-Gummel scheme. In a Schappeter-Gummel scheme, when a node or when an edge is given, then we can calculate our J sub n following this expression. Still looks quite much complicated. So in order to reduce the barrier for newcomers, usually we introduce a certain function called Bernoulli function. So that is given as x divided by exponential x minus 1. Please try to find out Bernoulli function in this J sub n expression. You can easily understand. Here we have something related with Bernoulli function. So can you recognize it? So when we say x equal to delta phi over Vt, then this yellow region can be immediately recognized as the Bernoulli function evaluated with the input argument like x or delta phi over Vt. So it is easy. So you have the argument and take the exponential of your argument, and minus 1 goes here. So now it is not that difficult to say this way. Any question? The next term looks more complicated because wow, here we have once again, let me just write down here. You can find the same factor. So this is nothing but just a Bernoulli function of delta phi over Vt. However, that's not the end of the story. Here we have exponential term. So exponential delta phi over Vt is involved. Actually, instead of this form, we can write down here. So this is delta phi Vt over exponential delta phi Vt. It is written as this form only because a special property of our Bernoulli function. Let me just derive this special property, like Bernoulli function of minus x. Let's try to evaluate it following the definition of our Bernoulli function. How can you evaluate it? So here we must have the input argument, so we must write down this way, minus x instead of a positive x, and exponential minus x is required, and take minus 1. This is the Bernoulli function evaluated at minus x, and by multiplying exponential x in this upper part and lower part simultaneously, then we can have 1 minus exponential x. Also, we have minus x exponential x. So irony. Then here we have a minus sign. This minus sign is just used to rearrange this lower part. Then x exponential x. Then what is it? X over exponential x minus 1. That is nothing but just Bernoulli function evaluated at the positive x instead of negative x. So exponential x. Now please have a look at this part. It is exactly in the same form. Bernoulli function evaluated at a certain value, certain input argument, and multiplied by exponential of same argument. This is corresponding to Bernoulli function of minus the input argument. So that's the reason why we just write down in this way. So simply speaking, this is nothing but just a form of this seemingly more complicated function. But in order to show you more compact expression, we just introduce this minus sign in the Bernoulli function. Otherwise, everything is just perfectly identical. So, do you have any question up to now? Yeah, please.
좀 지나가서 묻는 것 같긴 한데요. 혹시 그건 아니라 결국에 이 컨티뉴티 이퀘이션을 풀기 위해서 파이에 대한 값이 이미 풀어져 있어야 하는 거죠.
So his question, so let me repeat his question. So in order to solve this kind of a problem, we must assume the electrostatic potential. Because we always use this delta phi, and this delta phi is by definition the difference between phi sub I plus 1 and phi sub I. So anyhow, we have to have the previous knowledge on these node values of the electrostatic potential. So my answer to your first question is yes, we must understand the form of electrostatic potential already. Otherwise, we cannot proceed. So, is it everything of your question, or do you have any subsequent questions? So please go ahead. Okay, so as he asked once again, then how can you calculate these electrostatic potential values? So fortunately, we have already studied the equation called as Poisson equation. So by solving the Poisson equation, we can get some information about the electrostatic potential. Under the obtained knowledge for the electrostatic potential, now we can solve this continuity equation. But although this is your question is raised in this slide, but your question is nothing related with Schappeter-Gummel scheme itself. So even though we have quite a naive discretization scheme in our previous homework problem, even in that case, we must couple our Poisson equation and continuity equation simultaneously. So with the Newton-Raphson method. So then we can simultaneously calculate the electrostatic potential and electron density by solving the coupled set of equations. Okay? Good question. And if you have any further question, then please feel free. So it is more important to answer your question than just going ahead without taking any question. So now we have this well-known form K when we have the electrostatic when you have the electrocontinuity equation, we must evaluate the electron current density, and the electron current density is written as this form or discretized with this form. Okay, so this is really important form. Actually, in our lecture course, this is the single most important expression. You must understand this form, derivation of this form, and please.
대등의 함수는 어떤 의미를 가지나는지 이렇게 바꿨을 때 저 펑션이 들어간 이유가 있나요?
Okay, so that is also really good question. So actually, in the second next slide, I have drawn the Bernoulli function. So maybe you can understand, you can feel what is the meaning of this Bernoulli function. But right now, I cannot tell you definitely. So why don't you just wait for a while to see the second next slide. Really good question. And now, before showing you the Bernoulli function, I have prepared a comparison between our previous naive discretization and our Schappeter-Gummel scheme right now. So please understand, this is corresponding to what? Your diffusion term. And this one is corresponding to your drift term. So everybody can recognize this diffusion term and drift term quite easily. Please try to identify diffusion term and drift term. Which one is drift term and which one is diffusion term? So maybe you feel it is difficult to answer my question. In order to have any kind of diffusion, we must have the difference between two densities. But well, here this term itself is just proportional, only proportional to n sub I plus 1. And this term is dependent on only n sub I. Now, where is diffusion? Actually, diffusion is obtained by this difference between these two terms. Actually, this entire term is specifying the diffusion. Then natural question is, then where can you find drift? Drift is also involved with this difference of potential, then this one does contain potential difference. Yes, it contains potential difference. Then how about this second term? This one has the potential difference. Yes, also it has the potential difference. They are all related to the drift. So now you understand the beauty of this Shapiro-Gomez scheme. If we just approach this discretization problem naively, then we are just human beings. So therefore, we try to clearly identify the diffusion term and drift term separately. However, by taking this kind of derivation procedure, we have found a unified form where both of drift and diffusions are mixed up and efficiently and effectively working for each case. Okay, so please understand, in the case of this Shapiro-Gomez scheme, these two terms are merged. Okay. Another reason why I prepared this comparison slide is like this. In many cases, we just take the electron current density as a reference example, but equally important one is Hall. So don't be fooled by this Hall current density. Sometimes it is quite easy for beginners to make their mistakes when implement current density, because electron density, current density, or Hall current density, their current densities looks quite similar, and only difference comes from where here we have different sign, and where do we have also different sign? Here and there we have different signs. So this sign difference sometimes can be quite annoying and sometimes can be quite much error-prone. So it is really easy to make many mistakes. So please look at it. Then what happens in terms of our Shapiro-Gomez scheme? In terms of our Shapiro-Gomez scheme, here we have a difference. Yes, as expected. And how about the treatment of our this red colored term? Actually, we have n I sub 1, n sub I plus 1, p sub I plus 1. Their backbone is the same. So they share the same structure. And multiply by certain Bernoulli and certain sign swap. That is the thing we have to understand. Then what is the meaning of this input argument? This input argument is related with electrostatic potential, and it is related with the drift term. Okay, so the polarity, the opposite polarity between holes and electrons are reflected in this opposite sign of Bernoulli function. So please remember this one. Then now let's move to the Bernoulli function. So one student asked me the question about why do we have a Bernoulli function. So now let's have a look at it. By definition, Bernoulli function is given as this form: x over exponential x minus 1, and this is our x and this is our Bernoulli function. this one, this blue one is the Bernoulli function. And although it has quite complicated form, however, its graph itself or its behavior looks quite smooth, nothing special. So it is, yes. So let me just, in order to skip anything, I will just read this through because these properties are important. So zeros one. Why is zeros? Because it is unimportant, the most important quantity. Bernoulli function is positive everywhere. If we go to the infinitely large input argument, positively infinite large argument, then of course it can approach to 0, close to 0, but it is positive everywhere. Please note that when x equal to a positive number, this one is a positive number and this number is larger than 1, so their difference is still larger than 0. So positive number divided by positive number always gives you positive number. Same argument can be done when you have a negative number. When you have a negative x, this one becomes negative and this lower part becomes also a negative number. So it is true that you have just a positive number here. And how about x equal to 0? So when we introduce exactly x equal to 0, then this exponential function becomes really number 1 and this one becomes number 0. So 0 divided by 0 occurs. So numerically it is not possible to evaluate it exactly at x equal to 0. However, fortunately, when we make the limiting factor from x goes to positive x or x goes to negative 0, then they are converged to each other, so we can define the function form. So this value is just 1. Where can you find it? Actually, somewhere here you find this is really value 1. And another one is, if we go to the positive infinity, then what happens? Yes, this one is growing. However, we have exponential x. So compared with this exponential x, minus 1 or x, they are all meaningless. So they can be well approximated as x times exponential minus x. Okay, that's quite easy. And when you go to the negative infinity, then what happens? In this case, this exponential term will rapidly diminish. So we have nothing, so it goes to minus x. You can see that this is y equal to minus x, and you can see that your Bernoulli function is rapidly approaching to y equal to minus x when you have values like minus 4. Already they are quite close, and if we go to even lower number, then we will have almost coincidence between y equal to minus x and Bernoulli function. And another one is number 4. This is a function of monotonically decreasing property. Starting from here, it is just monotonically decreasing. There is nothing like going up again, always diminishing. And another quantity, property 5 is Bernoulli function. Of course, we can consider certain derivative slope of this graph, and this is given by minus half. Minus is nothing special because it is monotonically decreasing. So when you take any of Bernoulli function's derivative, then you will have a negative value. This is just a decreasing function, and the value is half. Finally, I wanted to say that careful implementation is actually needed for your real homework problem, because sometimes you say that I know that there will be certain problem when we have x equal to 0. When we have x equal to 0, then there will be certain error like 0 divided by 0. Yes, you are right, but in reality, even when your x is not as bad as exactly 0, but when you have an input argument a little close to 0, then you have a problem. Why? Here you have it, exponential something. So I mean that, let's say that x equal to, for example, 10 to the minus 17. Then what is the exact value of your exponential x? We can estimate it in this way, plus 10 to the minus 10 and half of 10 to the minus 17 square, and of course we will have the third term, fourth term, fifth term, whatever. But you know that since this number is quite small, 10 to the minus 17, so we don't care about this term and this term. Wow, they are gone. Then exponential of x when x is quite small can be well approximated as this number, 1 plus 10 to the minus 17. And we wanted to calculate this one, exponential x minus 1. Please try to calculate it. Then obviously everybody can say that, oh, that becomes 10 to the minus 17. Good, perfect. However, in your implementation, your numerical solver just calculate exponential x, and it does not make a distinction between your number exact 1 and your number 1 plus 10 to the minus 17, simply due to the limited precision. We are working with double precision number, so it's not possible for us to make the difference between just number 1 and number 1 plus 10 to the minus 17. So what is it? It is just regarded as number 1. Then taking the difference between number 1 minus 1, it becomes exactly 0. Then it says that, oh, something happens, so I cannot make this division by 0. So, you know, although in analytic sense, the problem only occurs at exact x equal to 0, but things are not that much easy. So we must divide our implementation into various pieces. So for certain range, certain form of Bernoulli function is used. For certain form, we must use another form. Careful implementation is really needed. So please understand. Since one student gave me a really good question, I think that it is a good time to revisit our Schappeter-Gummel scheme. Okay, from the behavior of our Bernoulli function, we can find out two different extremes. One extreme is 0 extreme here. Then Bernoulli function becomes just 1. And another extreme is infinite extreme. Then we have either 0 and either minus x. Let's consider these two extremes. So then let me just come back to this one. Well, when we have a 0 extreme, then how can we generate this extreme or get this extreme? It can be obtained when we have simply the potential difference equal to 0. When potential difference equal to 0, then this input argument becomes 0 and this argument becomes 0. Then please try to find out what is the form of this current density. Then we will have n sub I plus 1 times what? Bernoulli function evaluated at x equal to 0 becomes just 1 minus ni. Here we have also another coefficient Bernoulli function, but it becomes 1. So simply in this extreme case, we have ni plus 1 and I. The whole terms becomes just a potential difference. But let me revisit the meaning of this difference equal to 0. When we have no potential difference between two nodes, it simply means that we have no electric field. When we have 0 electric field, we only have diffusion. Then what happens if we have this kind of a situation? Then our expression becomes just q dn over delta x multiplied by delta n. What is it? This is nothing but just the first derivative over our electron density. So now it is approaching to q dn over dx. Yes, now we understand when we have 0 electric field, then Schapper-Gumbel scheme is just reduced to pure diffusion. Oh, good. It sounds great. Then now think about the case where we have infinitely large positive, for example, positive one. So this can be easily obtained by a condition like this. When we have delta phi, which is much larger than thermal voltage, then this one becomes positive infinity, and this one becomes what? Becomes negative infinity. Then when you have a positive infinity, what is the value of your Bernoulli function? Now you understand this one completely gone. Since the coefficient is gone, so this n sub I plus 1 term does not contribute to anything. Then now let's go to this ni term. Now you have a Bernoulli function of negative infinity, and you know that this one becomes just a negative input argument. Then negative input argument is just a potential difference divided by Vt, because here we have a minus sign. Vt delta phi. This is form of our bracket. Then what happens? Let me just write down here q dn over delta x times minus ni delta phi over bt. So when we consider this and that, delta phi and delta x, now we understand this is corresponding to electric field. And here we have Ni, and dN divided by thermal voltage is just given by mu n, and we have minus q. Have you ever seen it before? This is nothing but the form of drift term. So we are working with the balance between, or competition between, diffusion term and drift term. When we have a strong electric field, what will happen? The impact of a drift term will be dominant, and we don't have to consider diffusion term. So that's the reason why our Chappell-Gomez scheme predicts that when we have quite high potential difference, then the discretized form just reduced to the drift dominant expression. So simply speaking, I told you that this term does not have explicitly diffusion term, does not have explicitly drift term. They are all merged into here. And when we have certain cases, certain value of delta phi, depending on the size of you, or magnitude of your applied potential difference, it can be used just like a diffusion dominant one or drift dominant one. So Bernoulli function plays the role, the controlling, which operational regime is the suitable one for our operation. Okay, so are you with me? So since time is up, we have to stop here, but I think that fortunately we have covered many things, many important properties of a Chappell-Gomez scheme. So now let's continue our discussion. So theoretical one is already done, and now we have to do certain implementation. So my suggestion is, don't wait until the homework problem is announced. Now you know what will be the homework problem. The homework problem will be based on your previous naive implementation. Now you must implement much better Chappell-Gomez implementation scheme. So please start now, but the official announcement will be postponed to give you sufficient time to prepare yourself. Okay? So do you have any question? So if you have any further question, then please come to me after this session is over. Thank you for your attention. Bye.